Okay, uh, I hope you can visualize the screen here. Okay, we'll take this on the other side and we'll open up this screen. So this was our last lab where we started discussion about the filters, and we discussed how to implement an average filter and also how to implement an average filter using weights. For instance, something that you are seeing here, it only shows the implementation of average filter, simple average, uh, just by dividing the overall sum of the products by 9 here. But when you define the kernel with all the weights being same, then we we cannot divide it by 9, because in that case you individually divide each pixel product by 9, each pixel by 9, and at the end we just get the sum. So that is indeed sum of the products. So both ways we discussed here, you can choose different weights, either being 0.11 or 1 by 9. It's all same. And we also discussed that to implement any filter, we have to establish four loops. The outer two loops are used to traverse through the entire image, and inside the two loops, these loops here, are used to traverse through the filter area. For instance, if your uh, filter is 3 by 3, so there are 9 pixels in the filter area. So you have to pick up every pixel, read that value, and that then multiply that value with the kernel value, corresponding kernel value. So for example, the pixel at position I comma j will be multiplied with the pixel at position I comma j in the kernel. And we see here that we are only getting the red pixel here, right? Can someone explain that why we are only reading the red, getting the only red pixel? Why not some other pixels? For example, the green value or the blue value. Just a quick recap of the last lecture. I advise, if we, because we do not want the original color, so we want it grayscale. Uh, yes, we want to apply the filter on the grayscale. So where there is a call for this filter, uh, before calling the filter, you can call the function to convert the color image into grayscale, and then apply the filter on the grayscale image. So here we are assuming that the picture we receive is a grayscale. Last time I remember that some students may had a confusion here, that they converted into the grayscale after applying the uh, filter, average filter. But don't get it confused with that. Huh? So just make sure that first you convert it into the grayscale and then apply the filter on the grayscale image. And then at the bottom, we also discussed here, this was just to convert it into grayscale, right? And then at the end, we also discussed how to convert, how to apply the uh, average filter on the color image. So for that purpose, we don't need to convert it into the grayscale. We can directly apply the average filter on the colored image. So we have three different kernels. Sorry, three all the three sums. So you have computed three different sums for the one for red, one for green, and one for blue. So we calculate the value for each. The new value, make the color object using the new calculated value RGB, and then set that color into the uh, target image. So this way you can produce a uh, colored image, which is the, for example, here we pick a file, we can create an object, then we just display the original image, we convert that into grayscale, and then we uh, explore the gray image, just display the gray image. Then apply the average filter on the gray image, and this will produce a blurred image. Then we display the blurred image. And if you see here, we are calling the average filter on the color image, not the grayscale. So we call this color picture object here, this picture is called up here. So we created a blurred image which is colored, and then we displayed it. So before I go further, I can quickly run this and you will see all the outputs one more time. So for example, we pick up here some image here, for example, this one, and this is your original image, and this is your grayscale image. And then we have a gray blurred, and then finally we need a colored blurred. So this is how you can compare the blurred color with the original color, and this is grayscale of the original, and this is the blurred of the grayscale. So I hope it is a quick recap. Now we can move on to the Laplacian filters layer. Do you have any questions here from the last slide? Otherwise, we can continue. Okay, thank you. Let's close it down and then go to the Laplacian filter. Laplacian filter is almost very similar in its implementation, but the weights are different. So if you look at this part, for example, here we have defined the Laplacian edge detection, which is a binary. But before I move on, make sure you know the difference. Huh? Average filter do not detect edges. The filter is applied only to smooth the image, to make the image look smoother. This can help to some extent to remove noise. For example, some areas that might be posing some sharp edges, or they can be smoothed out. Huh? So you will see that there's a blurry kind of impact on the image. Laplacian does not blur it because at the end, what we do is that we uh, convert the image into a binary image by putting either black or white. So the reflection is used not to blur, instead it is used to detect edges. So we have the width and height of the image, and all time we always create a new image, duplicate, just to avoid uh, using the modified value, because when you apply the filter on the center one time, it will change, and you shift the filter to the right. So when you shift the filter to the right, now the new center will have one modified neighbor, which we do not want. That is why we create a copy, and uh, the copy image is used for writing purpose, and the original image is used for reading. So original remains same after each iteration. Now here we define the kernels. We have the kernel as 0, -1, 0, -1, 4, -1, and 0, -1, 0. Uh, if you remember, we have to understand that these coefficients are, this is kernel or filter, the same thing. These kernels values or coefficients are chosen based on the sum of these coefficients is always 0, because what we are doing here, we are multiplying by some weights the neighbors, only the horizontal and vertical neighbors, and producing a negative value, and multiplying the center value with the positive value. So you will see at the end we make a sum of products, and that sum of product will generate a difference. That means if there is a possibility, if there is an edge, then it will generate a some difference, and that difference could be greater than the threshold. But in case if there is no edge, these positive and negative values will cancel out each other. So they will show that they actually belong to the same area, same kind of uniform color, where there is no intensity differences are there between the center and the neighbors. So now we have established our outer loops to traverse through the image, and then we establish the inner loops to traverse through the filter area. And again, remember, this is a 3 by 3 filter, like the average filter. We can also generalize it, but I think if you remember, we have discussed this generalization effect in the class, which you have to implement it by yourself, and you can do that easily. Now you see here, the inside the filter area, you start always with -1 to 1, and this is also -1 to 1. So we get the pixel from the original image at position I plus dx, comma, and j plus dy. And remember this formula, that when you're reading the pixel within the filter area, that will be read within the outer with the outer. So you just add the outer index in the loop with the outer in the in the interior or inside, because we can just differentiate these four loops by saying that this is our uh, image area traversal loops, and this is our filter area traversal loops. So the outer of the image traversal is added into the outer of the filter traversal, and the inner index of the image traversal is added into the sorry, is added into the filter uh, inner of the uh, filter traversal area. So that's the actual formula here to approach uh, the pixel inside the filter. So we get the pixel here, and we calculate the luminance of that pixel by just adding these values. And these are the same lines of code that we saw in the average filter. So this time it should be more easier for you to work with that. And if you see here, when you have the luminance with you, so each time we multiply that luminance with the corresponding uh, value in the filter. And if I can show you here the convolution here, for example, look at this slide here. So we have now a filter here, and we are picking up every pixel in this filter area, the yellow portion, the yellow area. So the first pixel is first coefficient is multiplied with the first, and second with the second, third with the third, then second row with the second, then third row of the filter is multiplied with the third row of the filter area. So all of these products, so you need these products, and then you sum them up. This is what we are doing here. So these are all products, and their all products are added into the Laplacian sum, which was initialized at 0. So once you have the sum of the products with you, we can compare it uh, with the threshold we pass. So this threshold can be any value. If the Laplacian sum is greater than the threshold, this means the differences between the center and its neighbors is significantly high. That is why it will color, it generates actually a new color here. And we call that color as a black, because we are hoping that the edge will be black. We want to represent the edge that we determined as a black color. You can also define it white, but the non-edge will be then black. So our edge is black here, and non-edge is white. So else we define this color. So once the color is defined, you can set that color into the pixel. Which pixel? Which is the new picture. And new picture is actually the duplicate here. This is the duplicate. At position I comma j, and remember I comma j is the outer, is I comma j are the indices of the outer nested loops, image traversal indices. Okay, here. So we just, because at I comma j is the center, so we get the pixel at the center, and center is then modified with the new color object, and that's all. So this is our Laplacian. Now if you run this function, we want to call it, we pick a file here, we will take a picture here, then explore the picture, and then edge binary, call maybe for example just a little threshold 15, and then check. So let's run this. So we will display the original image and the uh, image after the Laplacian edge. So let's check this. For example, the same equal. This is the original image, and it takes a little while. And imagine that this is a 3 by 3 filter. Now we have the uh, this is the output with a 3 by 3 Laplacian filter. What do you observe here? If I can ask you uh, about this output. Here in this output, if you see, There are two types of edges. One is a global edges. For example, the global edges means those edges that retain the shape of the uh, object. For example, there is a tower here. So the tower is defined by these edges, the long, and that's it. So even if you preserve all of these, that means it's fine. So those global edges are determined, and they are perfectly defining the shape of the tower. But the local edges, for example, on the tower, there are lots of edges here, which are just determined as a noise, which is not good at all, truly. So, in other words, all the local features or the local information within the object is almost of no use for us. That information is not retained, because so the algorithm works only preserving the uh, global edges. Maybe if we can combine this approach with some other filter, we probably can get better results. However, we can slightly play before we adopt any other strategy. We can adjust these threshold. For example, I make this from 15 to say 20. I mean, I'm just increasing it slightly, not too much, and then see the output, how this is going to behave. Now the original and so we have so these are the three outputs. So that's the original. And this is again. Do you see any difference between these two? We have slightly raised the threshold. Maybe still we cannot judge that better. What if we can less local edges? Yeah, good observation. But still the global shape is retained. What if we can change that a little higher, maybe from 20 to, what if I can make it 35? Okay, let's not to display the original again and again and call that. Mhm. So if we can see that with uh, so here the threshold was 15, then we have 20, and then we have 35. So when you increase the threshold, at some point, if you look at even the global edges are also kind of started losing themselves, but still the original shape is still retained. We may need a descriptor here. We can describe this shape by taking some samples of the points. For example, at this point, at this point, at this point. Some we can pick up some sample points and then draw the curves. So when you draw the curves using these pixel points, this will just draw a shape like so. In graphic imaging, in computer graphics, uh, imaging tools, image editing tools like Adobe Photoshop, etc. You may see that this type of tools are there. So they detect edges and then they pick up some, they provide you the user interaction tool through the interface where you can define some pixel where you can just click on the pixel and that will draw. So we can retain the image. Okay, this is sensitive to the threshold. This is one thing. What if I go here and before I just instead of I just continue increasing the threshold, I keep my threshold the same. Is it possible, or how it is possible that I apply the Laplacian filter on the blurred image? So this means I want to call this average filter, this guy, where we have this S average filter, right? So I want to call this guy into this file and then apply the Laplacian filter. What do you think? Is it possible? So instead of directly applying that onto the original image, what if we can call here that function? For example, here the function is S average filter. So I just copy that and put that here. So I want to apply the Laplacian on the blurred image. So let's see. So S average filter will take up your original image and will return me the smooth image or blur image. Okay, blur image. Then I will pass this blur image to the Laplacian filter. Hmm. So we are having here import issue. So I think we can, our directory is here on the left side. This is our average filter .py and this is our Laplacian filter .py. So we can just go top and say that from uh, from the file name, that is averag filter, import what? Import a static, or I just name the function from the file average filter.py. Import just the function is S average filter. So we're just importing only one function here, and I think now that error is gone, the import problem. So S average filter will return a blur image, and you see here, what is that? Is there any display here in this? There is a duplicate copy, so this will return a copy image. Now this will return a copy image, and that copy image will be stored into blur image, and then we pass the blur image to Laplacian, and then we display this. Okay, if we can do one thing here, we can just explore the blur image. So we're now having, so I hope you guys understand what changes I have made into the code. We just want to see the impact of the Laplacian filter when it is applied on the original image and when it is applied on the blur image. I think I have still these outputs for the blur, for the Laplacian, and we will have here another output. But do not display this original again and again. Let's keep it off. Let's see. still have an original. This is grayscale. This is the grayscale image. Sorry, average blur image. Why it is opening up? I think that it is calling the main function from the average filter. We just did not control that. Anyway, let's try this. So it displayed everything there from the average filter. Yes, here is our last output. Please ignore all of them because this is because we have here, for example, here, go to the main, there is a lot of display here. So 1, 2, 3, 4, and so on. But let's compare them. This is the colored blur. And this is with the threshold 15. This is with threshold 20. And this is with threshold 35. And this is with threshold 15. Okay. But we have first applied the blurred image, the blur filter. Yes, I will upload. I hope you guys understand what is happening. Please clarify if you have any confusion. Can someone explain here the problem that why we have called up the average filter before applying the Laplacian? Because Laplacian was not that good. When you directly applied the Laplacian, so what we did, we just continued raising this threshold. And with that threshold, we arrived here. Still, we have a lot of noise in the output. The local edges, which are behaving like a noise. They are not noise, but for us, that's noise because we cannot interpret any significant output. Then what we did, instead of going on and continue increasing the threshold, we jumped, we went back to the same threshold, 15, but we called up the average filter. Now you see the local noise is almost lost. There is a very less noise, and still the original global shape is retained. That's very interesting thing. Okay, I think we can continue with this. I hope you can make further changes into this and play with that. Mm. Now after that, we have a Sobel filter. Before I start Sobel filter, I need you guys to ensure that if there are any questions, Iyad, Saud, Saeed, Abdul Rauf, Abdul Malik, Ali, Muhammad, Yusuf, Yusuf, Yusuf al Safi, and Yusuf al Jayya. I hope the discussion we made and the changes we made into the code make sense to all of you. Now we want to move on to the Sobel filter. Before I move on to the Sobel filter, the process is almost same. Huh? That's the convolution, the sum of the products. Huh? But I want you to take a look into the slides. It's the same convolution, but this was Laplacian, and then we have the, with the Laplacian, we can also define these coefficients. So that's how we can generate the intensity for the center, and then we calculate the intensity of for the neighbors, a collective intensity for all of them, and that collective intensity is then added into the central intensity. Now this is 8 times, this is also 8 times, but in the opposite direction. If that ends up with 0, that means both pixels, the center and the neighbors, they all belong to the same region. There is no change in the color between the center and the neighbors. So there will be no significant intensity change. But when there is an edge, it will definitely create a big difference. So the negative, when added into the positive, and this may create a difference if there is an edge. Similarly, that's another filter. I want you to try different filters, all of them. We only implemented this one. I want you to implement this one and this one also. You need to just go back to the Laplacian filter and change these coefficient, and then see the impact of these changes, the filter coefficients, how it is going to work. Okay, let's move on to the Sobel filter. The Sobel filter, it works the same way, but what it does is we have two different filters, one for the horizontal edges and one for the vertical edges. Here is the horizontal edge uh, detected, and here it is vertical edge that is detected, because when you compare the top and bottom pixel, minus 1 1 minus 2 minus 2, then minus 1 plus 1, then minus 1 plus 1 minus 2 plus 2 minus 1 plus 1. So this is like comparing the top with the bottom, top with the bottom, top. So whenever the top is compared with the bottom, but collectively, uh, it looks for the horizontal edge between the two. Then same way here, same way. So that's a horizontal edge. Okay. Now you need to implement this formula. That's a magnitude of the gradient. Gradient means the change in intensity, derivative. Now look at this. We have these gx and gy, these Sobel operators or kernels. In this case, we have a Sobel edge detection, but we call that binary because it converts the image into binary. Uh, you know, I will tell you one thing. On some places, you may find that the Sobel edges produce grayscale, not a binary image. But I will explain that at the end of the code, that why where we can keep it as a binary and where we can generate the grayscale. Let's look at this. We have a gx and gy, two operators are there. Now we will apply the two operators one by one. So we create the sum of the products for gx and for the gy as well. So we have outer loops to traverse through the image, and we have the inner loops to traverse through the filter area. So first we apply this filter onto the filter area, and then we apply this filter onto the filter area. Look at this. The pixel is the same. So pixel is the same that is extracted from the position I plus dx comma j plus dy, and this is from the original picture that was received here. Now, once you get the pixel, we calculate the luminance by dividing the sum of all the three channels by 3, and that's the luminance. So once you have the luminance from that pixel, we can multiply that value with the corresponding uh, position in the filter gx. So for example, here -1 is multiplied with the same pixel in the position. Maybe I can refer back to this concept here. We can go back like this. For example, here you have the weights. So you multiply this one with this. Then 1 by 9 is multiplied with 100. This 1 by 9 is multiplied with 108. Then this is multiplied with this. 1 by 9 is multiplied 106, and so on. This 1 by 9 is multiplied with 85. So once you have these multiplications, the products, at the end we get the sum. So that's the new sum that is calculated. So we have now two sums, sum of the one for x position and one for the y. So this is the Sobel operator. It's a directional. It determines the directional edges. If I only apply one filter at a time, for example, only gx, it will determine the uh, horizontal edges. And if you apply gy, it will determine the vertical edges. So to determine both edges, you have to apply them both at the same time. Once you have the sum of the products, then we take the square of the sum x plus square of the y, sum y. And then you take the square root, and that's the change. The gradient means the change in the intensity. So once you have the final change in the intensity, we can compare that against with the threshold. By the way, I'm keeping here the threshold just to make sure that we want to convert the image into binary, so that we do not have lots of color. This is my choice. You can also uh, keep it as it is, because the point is that the gradient is always a big difference. This is one major thing in the Sobel filters, that it will definitely create a big difference. So you don't need to have uh, all the time check that if the gradient is greater than the threshold or not. But just to make it binary, we check it against the threshold and create a color object, either black if there is an edge, and or create a color to be white. I want you guys to just focus on the binary images at the end. Forget about the grayscale output, how that is managed. But that's not that big deal. The whole code remains same. Just the and condition is not required. And then finally, we have the new picture, uh, get pixel at position I comma j. You can also write that in a different format like we saw in the Laplacian like this. You can pass the set color, and inside you need two parameters. The first is the pixel object, and then you have the color object. So here it is slightly different. Uh, the new picture, from that picture it gets the pixel, and that pixel, in that pixel then we set the color, which color that we just defined here in the threshold conditions, and at the end this is going to represent. Now let's apply this. Let's run this code and see how this is going to generate. Let's consider the same image so that we can compare with the Laplacian. That's the original, and yes, so that's the filter. And you see here the output, the threshold is value is quite high, uh, which we don't need. I mean, if I can just compare this guy, this is Sobel with 75, uh, and Laplacian here with the threshold 15, Laplacian 20, Laplacian 35, Laplacian 15 merged with simple average, and then we have the Sobel with the very high threshold. This looked like a draw with a sharp. Sorry, I did not get your point. You mean the it has it's like a wet pen. Ah, that is releasing it. But you see the global outer edges are very strong in this, very strong, right? That's the difference. Huh? So it depends again always what kind of application we are having and what kind of output we are looking for. So when the output are when the uh, output edges are or the global edges are very strong, they can be very useful. Let's try, because in that case the loss of information might not be, because here, for example, look at this. I want you to just see something. Can you notice the gap between this top of the tower and slightly below that? This is the gap, right? So we merged it with a very low threshold, but we lost some global edges. The global information was lost. But in all of these cases, here, even here, for example, here, that global is not lost, that global information. Let's play this with the little different threshold values. For example, here, what if I can make it again 15 and compare it with Laplacian field 15? So try this. Oh, now you compare that with the, this is your Laplacian 15 and this is Sobel 15. Now we change it. Hmm? Let's make it 20 Sobel. I need you to implement these all filters and notice the differences when you change these threshold or make some other changes. And now look at this, and this is really very black and completely. This is compared with Laplacian 20 with Sobel 20. And then finally we can make it 35, for example. Here, like we did in the Laplacian, just to put them in all one scale. Hmm. Now this is for Sobel 35, and this is Sobel 75. Sobel 75. What if I put 75 for the Laplacian? Huh? I can go back and change the Laplacian threshold to 75 and see how this is going to work. So it's a very high threshold. Oh, we should have closed the average filter. Not this one. Sorry. We need to block the average filter because this is all in combination with this Laplacian is combined with. No need to just switch it. I will block this guy. So it's not a blur image here, it's a picture. So now we call Laplacian with 75. That's the high threshold. And we need to block the main function of the other. This. Okay, now we can do that. Fine. So now we have a very high threshold with the Laplacian. Now listen. So the final, this is Laplacian with 15. Okay. Then we have Sobel 15, Laplacian 25, Sobel 25. Sorry, 20. Laplacian 20 and Sobel 20. Then Laplacian 35 and Sobel 35. And then we have Laplacian 75 and Sobel 75. Now tell me, what did you observe here? Can someone explain on what is going on? Which filter is, if I ask you for some reason that which filter is better, which one would you like to choose up? Mm, no, I want you to just notice. Let's forget about which one you will choose. Just I want you to first. First my question is simple. That what differences you note between this stream of output that was generated by the Laplacian filter with the increasing amount of threshold, and this is for the Sobel. So what is the difference you note between the two, between the Laplacian and the Sobel? That's it. So I keep my question simple, simplify. Hmm. When the threshold value is increased, you may you may have the uh, features. You may lose some information, some noisy information. For example, look at this. With a low threshold, the Laplacian was good enough, but there was a local noise, a lot of. But in the uh, Sobel with less threshold, there is a lot of noise, even the global outside outliers. That is even high noise, that is very high noise. There are lots of edges, because we are representing black with edges. So you see that it's all black everywhere, which is actually not the case like that. So it has completely lost the local information, if you see here in this case. So some design patterns are there. But when the threshold is increased, this the Laplacian not only reduces the noise but also loses the. It helps us in reducing the noise, but also lose the global information as well. But the good thing with the Sobel filter is that it not only suppresses the noise but also controls the or retains the global information. That's a very key observation in this case. You can use, of course, any one of your choice depending on the requirement of your application. If you still continue increasing the uh, threshold, I hope uh, you will observe more differences. For example, if I can go with Sobel instead of 35 here, let's say the last one was 75, I think. So if I make it, let's say 100, so what happens in the Sobel? Hmm. Check this. See, the beauty is that still it has all the global edges. Huh? Yes, exactly, exactly. But you see that the problem is the global information started losing here. It's because of, if you see in the even in the original image, this part is almost the same as the outer cloudy area. So in this area, the part of the tip of the tower is almost the same color, that is the color of the clouds. It's so thin, yes. Okay. I think uh, I hope you understand these changes. I have uploaded an assignment today, and you have to work with the assignment. Let me show you. You will be working with the generalized simple filter, hmm, and you have to create an interface. Generalized simple filter, a simple average means not just 3 by 3. It can be any size, 5 by 5, 7 by 7, or any order. For the weighted average, it is 3 by 3. For median filter, minimum, maximum filter, 3 by 3. Laplacian is 3 by 3. Sobel is 3 by 3. We have done both of them, all right, here. But you will implement them through the interface and then show the output so that user can manage. Yes, I will send it now. So the user can manage and see the output. So I will upload everything here in the learning material. I can go to the practical content. I think we have here some only average filter is there. No? Give it a second. I think maybe I can filters. We can browse the average filter, reflection, and it only allows me to pick up only one. Let me see if I can. Instead of creating a file, we create icon. Okay, no problem. Average, reflection, and then sober. Okay, so here are the filter one. Here only there was average filter, but here all the three, average, reflection, and sober. Okay, now do you have any questions here? There is your task for you for the Laplacian, that you will perform, change the filter coefficients and compare the output with different threshold values. Increase the threshold value, increase the threshold value from 0 to maybe 50 with a regular step. For instance, first pass the threshold value to be 0, then 5, then 10, then 15, then 20, then 25, then 30, then 35, then 40. That's it. So, and then put all the outputs in single frame like this, same like this, huh? So in single frame, and then show the differences, huh? And then again change the filter coefficients. Where are the coefficients, huh? The coefficients are here for the Laplacian here. So this one was implemented here, huh? The first here, this one. So you will change the filter coefficients with this one and this one, okay? And then generate the output. Maybe when you implement two, so maybe we can say 1, 2, 3, 4, 5, and 6. Until 25 is enough. So this is like you are going to have 12 outputs because you will change the filter coefficients. One first for this, you will generate 6 outputs. Then change the filter or the kernel to this, and then again change, generate the 6 outputs, and put them all in one screen. So one screen for this one, and the other for this filter. Okay, and then make a comparison and submit this task along with uh, the assignment, even though it is not there, but I will modify that later. Assignment. So you start working on the assignment, but keep this task in mind. Huh? This is just a comparative study for the Laplacian with the different kernel value. I hope you understand this point. Huh? In case if there is any confusion here, please let me know. Mm, do we have anyone here? For example, Saud. How are you, Saud? Are you there? Saud, can you listen to me? So, Saud, can you explain what I just asked you to do in the task and submit it with the assignment, filter assignment? Please feel free to use mic. Anyway, I hope you have followed the problem. I still hope, and I hope to discuss this in the class maybe tomorrow, and then later on, or even if we don't, our chapter for the filter is finished. So I will see that we have to start something new, or maybe if I possibly we need to just summarize, and we will discuss that tomorrow during the lecture on campus, inshallah. Uh, Now we can take up the attendance here. Yeah, we are starting the attendance by the way. Ahmad Alamudi, Abdul Malik, Yusuf Al Safi, Muhammad Al Harabi. Yes, of course we can talk. Saeed Al Zahrani, yes. Mhm. And Salman Bilhol, Salman is not here. Abdul Rauf, then Muhammad Sirajuddin, and then Iyad Al Sayyid, Ali Hamiduddin, and Saud is here, yes. And Yusuf Al Zayed. Yusuf, did you get the point? Did you get the lectures today? This is very important. Okay, good. I hope you will not hesitate in case if you have any questions to discuss. Just feel free, everyone, all of you. So just to quickly recap, we discussed a simple average which is applied on the grayscale image. This is just a grayscale. It's not a filter instead. Maybe we should not call this as a filter. It's just a grayscale conversion. But filter converts the image into something else. So we just name it as a filter. Then simple average on the color image without converting it into the grayscale. We have a simple average here. How will you transform this into weighted average? You need to activate this kernel, which we have just turned off. Okay. So there you will also activate the sum of the product. That's the difference. Then we had a discussion on the Laplacian filter with only one kernel, but I asked you to change this kernel and see uh, the output impact when you change the threshold value at the end. And then we also discussed the Sobel filter. Sobel filter requires two kernels, one for horizontal, one for vertical edges. And you create two sum of the products, and at the end we calculate the magnitude of the gradient, means the change in intensity. So we check the change in intensity. If it is below or above the threshold, if it is above the threshold, we say that there is an edge. We create a color object being 0. And if it is not, then we create a color uh, to be white and put that color into the pixel at the center of the filter in the new image or in the duplicated image. And that's all. Thank you very much for being here. Inshallah, we will continue. There are, by the way, a couple of more filters at the end in the lecture slides. After the Sobel filter, there is a private filter and there is a robot filter. Private filter has a change in the coefficients, one for vertical and one for horizontal. And the robot filter has only 2 by 2 uh, filter area, and you will just calculate gx and gy and then see the magnitude difference. Calculate the magnitude of the two convolutions. So you can implement this as well on your end, and this is of course included, but it is not given in the assignment. So I want you to do some practice. In case if you feel any trouble, just let me know. Uh, then we can carry on our discussion further. And you can also compare the output of all of them, Laplacian filter, Sobel filter, then Privet filter, and the Robert filter. Pick up only one image and see the impact of all of these filters. Except the simple average and weighted average, all the other filters, Laplacian, Sobel, Privet, and Robert filter, all of them, they are used to detect edges. Okay. And that's all. Thank you very much. See you inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, dear. Thank you. See you inshallah.